In topic 10 part 3 we're going to look at applications of finding the maximum and minimums. A lot of these problems have the same process that you should follow. Draw a picture, it gives you an idea of what's going on, and then convert the picture into maths. Now in this one it tells you you've got a sheet of metal and you've got little squares cut out from the corner, and then the sides are bent up to make an open box, a kind of a tray thing, and you've got to find the maximum possible volume of the box. So that's the thing that you need to work with, is the volume. So we need to get a statement for the volume. And the volume will be, the depth of it will be x, then the length of it will be 12 minus x, or 12 minus 2x actually, because you take off x on each side, and the breadth of it will be 20 minus 2x. So there's our volume statement. We need to either multiply it out or use the product rule in a short moment to differentiate it. Either way, we need to find the derivative, and the derivative is going to be 240 minus 128x plus 12x squared. And for maximum or minimum, that's got to be equal to 0. So we need to solve that, and that gives us the values for x of 8.239 or 2.427. Now we just need to think about it. 8.239 is going to make things a little bit odd if we look at the crosswise direction. So 12 minus 2 times 8.239, that doesn't work. So that answer is not going to be sensible. So we just need to check though what kind of answer we've got for x equals 2.427. We want to find the maximum. We don't want to end up finding the minimum. So we need to find the second derivative and then find the second derivative at x equals 2.427. So we differentiate the first derivative again, and then we substitute in 2.427, and we find that it is negative. So that tells us there's a maximum at x equals 2.427. It does ask you to find the volume, so you need to read the question. All we need to do with the x value now is put it back into the volume expression and find that the maximum volume is equal to 262 and a bit. And look at the units, it's centimetres by centimetres, so it will be centimetres cubed. This is a question where we don't actually need to use calculus if we don't want to. You're asked to find the current, and the current is the rate of change of the charge, and you're given the charge, so the current then would be dq by dt, which would be a 50th times 250 pi cos 250 pi t. Now the power, I suppose we could cancel that out and make that 5 pi cos 250 pi t. The power is the voltage times that. And we're told that the power is 100 sine 250 pi t, and we've now worked out that the current is 5 pi cos 250 pi t. So we just need to multiply them together, and our end result is 500 pi sine 250 pi t cos 250 pi t. Now, we can do a little bit of trigonometry using a trig identity there to prove or to show that actually that's equal to 250 pi sine 500 pi t. That's using the identity that says that sine 2a is equal to 2 sine a cos a. Now we can look at that to answer the next question. It says find the maximum power. Now the maximum power is just going to be that number there, 250 pi. We could go through the business of differentiating and making it equal to 0, etc., etc. But by just thinking just a little bit, then we can save ourselves a whole lot of work. So the maximum value there must be the amplitude, which is 250 pi. Now we're starting to get into the interesting questions. We have a rectangle. That's interesting. Let's just leave it there. Let's go back here. Let's rub that out. No, it doesn't want to be rubbed out. Okay, that's fine. Let us draw a rectangle. And let's make it X and Y, doesn't really matter. But what it does give us, it gives us that the perimeter is 2x plus 2y. And that, we're told, is equal to 40. That means we can get a statement for x and y. We can say that x plus y is equal to 20. Now, we're trying to maximize the area. We know that the area is equal to xy. So what we would do is we would find the derivative, make it equal to 0, but our problem is that a is not just a function of x, it's a function of xy. So how are we going to get past that? Well, here is the answer over here. We've got that x plus y is equal to 20. So from there, we can say that y equals 20 minus x. And we can put that in our area statement. So now we can say that the area is equal to x times 20 minus x. and we can go from there. That's 20x minus x squared. Now we can find the derivative. Set it equal to 0 and solve for x. If we do that, we get that x is equal to 10. If x is equal to 10, put it back in the original one, then y is equal to 10 as well. Now, we're asked to find the maximum. So we'd have a maximum if the second derivative was negative. So we need to find the second derivative. Okay, the second derivative's just going to be negative 2. And that's negative. We don't actually really need to know that it's negative 2. It's the fact that it's negative is the thing. So therefore, we've got a maximum at the point with the measurements 10. Oh, the pen is stupid. Right. Do we need to find the actual area? Read the question. Find the length and the breadth so as to enclose the maximum area. Nope, we found it that the measurements of the rectangle are 10 by 10. Now, a lot of you will be screaming at this stage that we have a square, and the question said find a rectangle. Well, that's fine. A square is a rectangle. A rectangle is something that has 4 sides. It has 2 pairs of sides that are equal in length, and it has 4 right angles. A square has all that, as does a rectangle. So in this case, the answer is actually a square. Same sort of process. We find a statement for what we're given. We're given that the volume is 200 cubic centimeters, and we know that the volume of a cylinder is pi r squared h. And we're actually looking for the surface area. That's the fact that we're given, but we're looking to find the surface area. To minimize the surface area, we should know that that's equal to 2 pi RH plus 2 pi r squared. What we'd need to do to find the least surface area would be to find the derivative of S with respect to, well, R or H. Let's find it with respect to R, but our surface area relationship has H's and R's into it. So what we need to do is we need to go back to the volume statement, which is a fact, and find that H is equal to 200 over pi r squared. Then we can substitute that into our surface area function, and we get a derivative and now that's going to equal 0 for our max or min. Right, solving that gives us that r cubed is equal to, what's it equal to, 100 over pi. And therefore that r is equal to the cubed root of that. If it's important to us, then we can use our calculators to find that that's equal to approximately 3.169 centimeters. We need to find H. Well, that's easy. We can put it back into the statement that we've got for h. We just put in 3.169. Actually, we should put in the cube root of 100 over pi to keep it accurate, and then we'll find that h is equal to 6.339. Like that, but we don't know for certain that it is the minimum, so we need to find the second derivative. So we need to find the second derivative, and we need to put in r, so we need to differentiate s for a second time, and then put in r, and what we find is that it's positive, so therefore we have a minimum when r is equal to 3.169 and h is 6.339. Now that's interesting. That's a cylinder whose diameter and height are the same. So that's the shape of the cylinder that's going to actually give us the least surface area. Draw a picture. You're going to have a straight wall that's already there. And then you're going to put in a fence around a paddock. Like that. And it's that fencing that's going to be 100 meters. So if we use that as y, once we've drawn the diagram, then we can work out a statement for P. So x plus 2y is going to be equal to 100. Now we've actually asked for the area, so that means we need an area statement. And it's actually that we need to maximize. So we need to find the derivative of A. Let's find it with respect to y. But we've got a problem in that our A is written in terms of x and y. So what we need to do is we need to say that actually x is equal to 100 minus 2y. So now we've got an area statement that says 100 minus 2y times y. And now we're able to differentiate that. So our derivative now is 100 minus 4y. And that's equal to 0 for our maximum. Solving that gives us that y equals 25 and that x is equal to 50. Now both of those are in meters. We need to check whether it is a maximum, and we do that by looking at the second derivative. The second derivative is -4, which is clearly negative. So therefore we've got a maximum area where x equals 50. It's a meter, and y is equal to 25. I've drawn the diagram for this particular question, but in an exam you wouldn't have been given that diagram. Sometimes they scaffold the questions and they say draw the diagram, other times they don't, and you're just expected to do it. So read the question, figure out that the surface area is equal to 2x squared plus 5xy and it tells you that that's equal to 6, and you also know that the volume of a box is equal to, in this particular case, x squared y. Right, what you're going to have to do is you're going to have to find a value for y from equation 1. So y is going to be equal to 6 over 5x minus 2x over 5. And then you're going to put that into 2. So that goes into there. And then we're going to differentiate once we've done that. And differentiating that, we get 6 over 5 minus 6x squared over 5. And that's equal to 0 for a maximum or minimum. Okay, solving that, we get x is equal to plus or minus 1, but of course negative 1's not sensible, so the only value is actually x equals 1. We need to check for the second derivative, and we need to check where x is equal to 1. Transpires that the second derivative is negative, so that tells us we've got a maximum when x equals 1. Check the question. Find the maximum volume of the box. All we found so far is the x value. So now we need to put x equals 1 back in the volume statement and in the y statement as well, and work out that v is equal to 4/5. This is an old exam paper, our old exam question. Find the derivative, make it equal to 0, solve it for t, and you find that t is equal to 25 seconds for your maximum or minimum. And then we need to check for our second derivative. We find that the second derivative is actually just negative 0.02, which is negative, so therefore there must be a maximum at t equals 25. So the question says, at what time does it begin to cool? The answer is the liquid begins to cool after 25 seconds. To solve this question, you really need to draw a diagram. So you've got a fence, like that, and it's divided like that, and you've got A1, you've got A2, and what you need to do is to label the bits, and you need to label the bits, say x and y, and work out then from your statement that you get 3y plus 6x is equal to 150. So that would be y, that would be y, that would be y, that would be x, and that would be 2x, and that gives you the bits that go together to make the security fence. The area, he wants to maximize the area. You work out an area statement. So the area is going to be 2x by y plus x by y, so it's going to be 3xy. We need to find the derivative of that, but we can't because it's got x and y, so we need to replace one of the variables with the other, and we can tell from the first equation we can write what y is. We can write that y is equal to 50 minus 2x. Like that. So now we're going to put y into here, and we're going to differentiate it. (150 minus 12x). Make it equal to 0 for your max or your min. And you'll find that x is equal to 12.5 meters. Now we need to find y. We can find that from our statement above. We also need to check the second derivative. If we check the second derivative when x is 12.5, we find that it's negative, so that we've got a maximum area when the dimensions are as that. This is a practical example of the earlier question where we had the cylinder had a volume of 200. So you can complete this one by just changing 200 to 330 and working it out. Now what you find is that the dimensions, as we did in the earlier one, the dimensions are really weird. You end up with finding that the diameter is the same as the height. You end up finding that the radius is 3.74 and that the height is exactly twice that of 7.49. Now if you look at it, that's not the shape of a Coke can where the diameter and the height are the same. Clearly there are other reasons for making a Coke can the shape it is, other than just using the surface area to be minimum. Look at the diagram on the next screen, and again we've got two functions. We've got that the area is equal to 2RL, and that the length of the track, what are we going to call that? The length of the track is going to be 2L plus 2 pi r, and that's got to equal 400. That gives us an expression for L that we can put into there, and then we can differentiate A with respect to R, and we make it equal to 0, and we find that R is equal to 31.8. And we use that to find the length, because rearranging equation 1, we can get an expression for L we can find that the length is actually equal to 400. And that shouldn't be a surprise because that's actually how they work out the size of a track. Oops, daisy, sorry, not 400, 100. Doing these sort of questions has a distinct process. First up, read the question. Probably you should make a diagram, draw a diagram. And for some of us, it's easy to see what we're doing if we've drawn a diagram. You need to define any symbols, define the X or the L or the B or whatever it is that you're going to do. Express the thing that you're going to maximize or minimize as a function of the X and Y or whatever. Now, we're going to then notice that we've got a problem, we've got two variables, then we need to eliminate one of them, and so now what you need to differentiate is just in terms of one variable, find the derivative, differentiate, set it equal to 0, find your X value or your Y value, whatever, then use that to find the other one, put both of those into your volume if that's what you're finding, or your surface area. Also check your second derivative to make sure that you have indeed got a maximum or a minimum.